actually say SETL, you just say set. So there's two different mnemonics that mean the same opcode, and vice versa. You also talked about how in an add instruction you say add $x, $y, $z, but since z is just a byte, we can just have the computer treat it like an integer rather than a register number, and we just drop the $sign from the mnemonic, or from the symbolic representation of the whole instruction. So we use the same mnemonic add, but it actually has a completely different opcode, right? One of them is opcode 20, the other is opcode 21. So the same thing at the assembly language level turns out to mean two different things at the machine code level. And Knuth celebrates this. This is awesome. This is great for the programmer, that they can write the same thing and have it mean two different things. Or write two different things and have them mean the same thing. Isn't this great? And I think for a lot of students, this is awful. You really do not want to have the same thing in two different, contexts mean two different things, when the difference is just like, doesn't have a $sign behind it. And I think that is adding some friction. Certainly last week, it took quite a few go-rounds to say, oh yeah, okay. If I add or remove a $sign here, that adds or removes +1 to the opcode, and then that causes the computer to do this other thing.
Yeah. So, as we know, it is dense. He packs a lot of content into just a few words or even mnemonics, as you can see. And I don't know how many of you had a chance to look at the table of the complete instruction set, but unpacking even that is a bit of an effort at first, because he's got multiple. So he's got this grid, rows and columns that stand for the hex value of a byte, but then within each cell there's partitions that tell you what that particular value maps to in terms of the actual instruction. So you have to read it really carefully. But let's go ahead and just go over the branching pieces from before, because even if you've seen it before, I think it's a good review. Definitely for me, it will be. And since Miguel wasn't here, and I don't know how much time you were able to spend, Arthur, that might be good. So let's look at. Let me pull up my slides from last week. Okay, so let's try this. Yeah. So let's start with that, which is kind of what Arthur was referring to. These instructions that let you use constants instead of registered numbers. So we'll spend about 5 minutes on this. Okay, so Michael, do you want to go ahead and maybe summarize the section?
So it's just the different ways of branching and conditional branching.
I meant the immediate constants section that we were just reading.
I guess my page numbers are wrong because I was looking at.
Oh, you have the older second edition, is that right?
I don't know what I have. I guess the section, the closest.
Oh, no, sorry.
Anyway,
it's my fault. This is the Fascicle one.
That's what I'm looking at. Yeah.
Oh, really?
Yeah. But the immediate instructions, I don't know where they are. The immediate instructions are the same as the regular instructions, except that the last part of it can be an immediate number, and it operates just as if that number were loaded into some register, except it's not taking it from a register; it's taking it from the instruction itself.
Yeah, that's great. Any other comments or questions, clarifications?
Yeah, I got a question. Where is it in?
It's right
immediately before the section.
It's right before. Like the last few words are right before jumps and branches. The last sentence of the section.
Yeah. Okay. That's fine. I got it.
I find interesting the whole wide stuff.
Yeah.
So what I understand there is that they, given an octa, you are taking like a smaller. You're just modifying the octa using a smaller word, right? Depending of. So, but I don't understand the medium IA is the size of the Y that you're using. No, the Y is always the same size, right? It's just two bits.
That 2 bytes. Yeah.
2 bytes. Sorry.
Right. So we've got a byte, which is 8 bits. We've got a wide, which is 2 bytes. Then we've got a tetra, which is 4, and then we've got an octa, which is 8. And tetra is significant because the instructions are tetras, right? All instructions are 4 bytes, so we do end up, using tetras a lot in terms of addressing for jumps and branches and things like that. And then bytes obviously are really important because they're the basic unit of addressing. And they're also generally, if we're just dealing with ASCII characters, then a single byte is all you need for an ASCII character. So those are also really important. And then octas are important because that's the width of the register and just the general sort of word size of the MMIX. And wydes, I guess wydes are, like, somebody want to say why wydes would be interesting?
So maybe answering my question about what does this set high, wide, and medium high might help to understand why they are interesting. So I trying to get some intuition about what's happening, for example, with set high, wide. So Y and set are supposedly both octas, right?
Each of them are bytes, but
just bytes, like two. Okay, so they are regular bytes.
Each of those bytes is normally treated as a register number. Right? We have 256 registers. So we have Y, and we say that identifies a register, this identifies a register, and each of those registers holds an octa. But if we're treating them as immediates, we treat them as literally just the bytes. We say, okay, here's a byte, we put them together, now we have 2 bytes. And we don't.
And that's a Y. Okay.
Yeah, 2 bytes is a Y.
But that's true for all of them, right? So when they multiply by 2 to the 48, you are just making a bunch of zeros, just padding it, or what? What are you doing?
Yeah, you're shifting it over with a bunch of zeros, yeah.
I see. So you're padding different size. So when you pad with different number of zeros, and then you make it. So what's the point of doing that? So I was assuming that you were. This is what I assume.
What's going on here, right? When you look at the register X, and that's still we're going to treat that X as a register number. So we're going to set one of the wydes of X. X is an octa, and so you can think of an octa that's 8 bytes, and so it's like 4 wydes right next to each other. We're going to identify one of these wydes, and we're going to put a value into it. Which wide are we going to put a value into? The high wide, the medium high wide, the medium low wide, or the low wide?
That was my assumption. I was trying, so it's great that you confirm it. I was trying to understand how that happened, but I'm fine with confirming it. I was trying to understand why. I still don't get the. I guess I'm fine with that.
So we use the 16-bit number YZ, and we slide it over by padding it with zeros. Right? We just keep adding zeros on one side of it until it's over to the place we want it to be.
To the place that you want to be. Yeah, that makes it. So, wait, so you put the zeros to the right of the XY? Is that what you're saying?
Yes.
Oh, okay, that makes that's what you. Oh, okay, yeah, that makes sense. That makes sense.
Just like you multiply a decimal number by 1,000,000, you put zeros on the right side.
Yeah, I'm still struggling with intuition on binary operations. When you multiply by 2 to the whatever, I still don't get it clear in my head. But that helped a lot.
Yeah. Base 2 is just like base 10 if you're missing 8 fingers.
Okay, so yeah, I think that's a good start at the explanation, but it takes a while to figure first of all, what is exactly meant by these instructions, and then, as Miguel is wondering, like, what's the point of these instructions? And so if you think of the register as 64 bits divided into bytes, we have actually 8 bytes, and so I would like to actually number them from the right. So 7, 6, 5, 4, 3, 2, 1, 0. Okay, so if you think of the register being divided into 8 pieces, each one of them is bytes. And let's say that 0 is the low end and 7 is the high end. So now one of the points of these instructions is that you can use a combination of some of these instructions to set a register to any value. You can start with any value and you can modify it within the register without having to load any data into the register, right? And for that to happen, you need a way to set individual bytes or bigger chunks of bytes, right? So that's what he's doing here. So when he says set high wide, right? So set high, this is going to set bytes 6, or let's say bytes 7 and 6, right?
Yeah.
Set high does that. Set medium high sets bytes 5 and 4. Do you agree with that, Miguel? And so you can then set, any piece of this register by using one of these set instructions. And if you wanted to set just a byte, you could still use the 2-byte value, but just make it a little bigger if you wanted to, the constant that you're using. And then you can increment. So let's say that you first set a value and then you needed to somehow add something to that value so that it allows you to keep that existing value and then set some other piece, some other part of the register. And so all of this is summarized in the bottom of page 14, where he says you can pick any 64-bit value and I can put that in a register without actually loading it from memory by using some combination of these instructions. So it's really useful if you are dealing with some values that somehow have been generated in the assembly language. Either you've written them yourself or maybe the compiler generated them for you. And you don't need to pull them from memory or have them located in memory before you do that. So that's my explanation. Anyone have anything further to add? Okay, so let's go on to jumps and branches, which is page 15 and 16. Spend about 5 or 6 minutes on this. Okay, so Arthur's made a couple of really great points, things that you kind of really need to think about a little bit and may not realize what's going on when you first read it. So I would definitely recommend that everybody reads those in the chat. But anyone willing to summarize what this was about?
Not summarize, but I want to ask just to make sure that I understood something.
Go ahead.
In the second and first and second paragraphs. So in the 1008 example, in that case, the next, if you are in 1000, whatever however you say that in Excel, the next would have been 1004, right? So by multiplying by 2, saying just go one step further than the one that you would have got. Okay, I got it. Right.
I don't think I followed the question.
So I was trying to understand the whole playing with numerics, because when the first time I read this, when it said add is where you are, so it's the whatever address you have, which is the number.
Yep.
And it says just the next instruction would have been where you are plus 4, because we are in tetras. It took me a while to wrap my head around that. Literally adding 4 is just like jumping the whole like chunk of bytes of bits to the next 16 bits.
Right, multiplying
Right.
by 4.
No, adding 4.
We're adding 4 times some number, which is the number of instructions that we want to jump.
Wait, what?
So because each instruction is 4 bytes, that means if you want to jump one instruction, that's 4 times 1. You want to jump 2 instructions, 4 times 2, 4 times 3, 4 times 4. And remember that even though it says plus 4 times 2, because of the arithmetic properties of plus and times, we have to take the 4 times 2 first. So think of the parentheses around 4 times 2.
Yeah, no, that was my question, and Arthur kind of like with his head he answered it.
Oh, okay.
And you confirmed it. So
Yeah.
I'm thinking.
Correct.
Yeah, this is actually, he's written this. I do feel it detracts a little bit on initial reading, because if you don't think about the opcode, or if you don't worry about the opcode, I find it much more understandable without the opcode mapping. Like if I didn't have to worry about the actual machine code representation and the bits that are generated for this instruction, I find it much more understandable. So if I ignore that piece, but to really understand what's going on, yeah, you do need to understand, like what Arthur is pointing out, that there's some calculation that's happening based on the symbolic form that you've written and exactly what that expression is. So if you're using some absolute number like 1008 instead of some formula that involves at, then what that opcode generates will depend on where you're jumping from, because there's this implicit 4 times whatever that number of instructions is being incorporated in that mapping. So it's kind of hard to explain, and I feel like it's an extra level of detail that on first reading I would be okay with if this was not there and it was some footnote or extra thing that you would read. Anyone else?
Yeah, so the thing that I was going to add in the middle of that, which I've now put in chat, is here's another example of Knuth code switching between different representations of the same thing. When we say hash 1000 or hash 1008, and by the way, those are hex numbers, so really hash 1000, I should be saying hash 4096 or whatever it is. Those numbers are counting bytes. He measures the MMIX is a byte addressed machine. Every time we write down a memory address, we're talking about the index of a particular byte in memory. But when we execute a program, the program is composed of 4-byte instructions. And when we execute one instruction, then we go 4 bytes on to get to the next one. We don't execute address 1, address 2, address 3, because then we'd be we'd be overlapping our instructions. When we execute a program, we actually run the code from address 0, address 4, address 8, address 12, skipping 4 bytes at a time. And so the jump instructions in coding, that's where that multiply by 4 comes from. He says, well, we're always going to be jumping by some multiple of 4. So let's just take whatever they put in the bits and multiply that by 4. No one's ever going to jump by 3 bytes, because that would just be nonsense at that point. So sometimes we see a 4 times, and sometimes we don't see a 4 times. And Knuth is kind of going to expect you to treat them as like, okay, yeah, I understand this is implicitly multiplied by 4, this isn't, etc.
I think another thing that I realized was that jump is a relative address, right? So you're somewhat limited as to how far you can jump because it's relative. There's just some maximum address and minimum address that you can jump to from any point. You can't jump to any arbitrary address. And to maximize the range of jump, right? Like if he said, don't use this formula, whatever you literally write is what we will allow for a jump, then you can see that that constricts the range of values that you can fit in the 3 operand space, which is 3 bytes, right? With this relative addressing scheme, with that formula that's built into sort of the calculation, I feel like he's extended that range. He's now allowed for a bigger range for relative jumps. Of course, if you wanted to jump to any particular address, then you could just use Go, because Go is a full-fledged 3-register operand instruction, and so you can calculate or come up with any address because each one of these registers is 64 bits. So that was my other take on this. So Arthur is pointing out Conway soldiers. Is that referring to John Conway, the mathematician?
It is, yes.
Okay.
And it's completely unrelated to MMIX, but
yeah, but it's if you mention anything Conway in the context of Knuth, it's always relevant because Knuth loves Conway, and he's gotten a lot of stuff from Conway over the years, and we will see that in the book as well. Many of the exercises will refer to Conway, but yeah, very nice. Look at that later, or whoever wants to look at it now. Anything else? Any other questions? Now, I will also say that I found this, pretty hard to digest, like at the first reading. But when I actually started to look at the programs and see these instructions in use, then they made a lot of sense to me, and I was able to, sort of internalize their usage. So when they are just standing by themselves and you have RA or you have, at in there, it gets a little abstract. So I would say if you have still some further lingering doubts or questions, maybe wait till we look at the programs and we'll actually step through these branches and you'll see what's happening. Okay, so where are we at now? 253. Let's start with the next. Let me see what else was there from last section. Yeah, so there wasn't really anything else left over from last week's agenda. There's a summary of the table and there's some timing information. Nothing too critical. There is this interesting section that follows the jumps and branches section, which is called subroutine calls. It's starred, so it is optional according to Knut's notation, and but it's worth reading if you get a chance at some point, because we are going to use some of these facts in the programs, and my plan is to come back to subroutines maybe after 3 or 4 sections of the algorithms and data structures volume 1 sections, because we don't really need the subroutines, or at least we don't really need to understand the details right away. We can just take it on faith. But at some point, it'll be nice to really understand how a subroutine works, which is essentially a function call and return back to where the function was called. And then even more interesting is the section, I don't know if it's in here or the next major section, which is coroutines, which is a really sort of fascinating feature of MMIX. But that, again, we can defer to, I think, at least like 6 or 7 meetups away. So right now, what I want to do is we're going to switch to volume 1. So we're going to move away from Fascicle 1 for just a little piece. I forgot to prepare a slide on this, so I'm just going to post that in the chat. It's this little algorithm in section 1.2.10 titled Analysis of an Algorithm. And this is, again, in volume 1, the main Art of Computer Programming text. And it just describes a little algorithm for finding the maximum of a list of numbers. And then we'll come back to Fascicle 1, which has the program that implements that algorithm. So the algorithm is straightforward, but it's still worth reading, I feel. And especially in the context of MMIX when we look at the program. So let's spend maybe like 3 or 4 minutes on this till 3 o'clock. And then if there's anything to discuss, we'll discuss that. Otherwise, we'll take a break and we'll come back. Okay, how did that go? Did it turn out to be as easy as I was describing it, or did you find some quirks in it?
Were we just reading the algorithm or the whole discussion?
No, no, no. Yeah, just the algorithm, just that. What is it like?
M1 through M5.
M1 through M5, like 10 lines at the bottom of page 96. Um, yeah, just that, because you're right to point this out. He uses this algorithm to introduce the full-fledged analysis that he will be doing for a lot of the algorithms. But we will come back to this analysis aspect later. But right now, I just wanted to look at the program that implements the algorithm and just set the context for that. So, Arthur, you did have a comment. Implicitly requires that n is at least 1, and indeed, if n is less than 1, algorithm M does bad stuff. Yeah, these are fair points. So I think in the interest of sort of focusing on the algorithms and not really adding a lot of other stuff. I've noticed that in many of his programs, there are a lot of these assumptions about very specific ranges. They're mathematically defined, but that's sort of like the prerequisites or the preconditions that are supposed to exist. And there's rarely any error checking or that kind of stuff. So yeah, you do need to be aware of this. Like if you were actually using his algorithms to implement or write something that's going to be used by people, you would need to add a lot of stuff. But it would take away from the main thrust of the actual algorithmic technique. So yeah, so any other comments or questions? If not, then
To
let's
clarify
take.
on mine,
Yeah.
that the thrust of mine was not so much that the physical algorithm lacks error checking as the statement of the problem doesn't really tell you what's supposed to be an error. You have to really read between the lines and say, well, he just said given n elements, but oh, I see. Okay, we're going to number them 1 to n, so I guess n has to be at least 1, or it doesn't work for empty sequences. But things like that, which he could have done. Right? He could have just said given n greater than or equal to 1 elements, with an addition of 2 characters. But, so the problem statements have these implicit requirements that you need to sort of read in.
Yeah. Yeah. Okay, so let's take a break till about 3:14, and when we come back, we'll look at the programs and step through them in the debugger. Okay, we're back. And whenever everyone gets back, we can start with this section in Fascicle 1 again, back to Fascicle 1 MMIX. And this is pages 28 through 30, section 132 prime, program M, that implements the algorithm that we just read before the break.
Call from Ketchup Robin. Call from Ketchup Robin.
Okay, so there is quite a bit in those few pages, but I think a lot of it really makes sense when you're actually working with a program. So it's nice to read, like at a first pass. You don't need to get everything, since it's talking about a lot of practical stuff that you will need to deal with when you're actually writing the assembly language programs. But is there anything that anyone wants to point out or ask questions about before we step through the program, and we can discuss the program along with the step through?
So I will point out something that strikes me as surprising to a programmer who is not familiar already with assembly language. In algorithm M, on page 96 of the main book, he does this as a sort of a while loop with the test at the top. So step M2 says, if we're done, then terminate. Otherwise, do M3, M4, M5, and then go back to M2. And he tests at the top of the loop. In the assembly language program, he deliberately puts the test at the bottom of the loop. This is idiomatic in assembly, that we're going to just sort of run through the whole loop, and then when we get to the bottom, either we're going to jump back to the top, or we're just going to fall out the bottom. And this saves us a branch. But it means that the structure of the assembly language program doesn't match the structure of algorithm M. There's no equivalent of M5's like return to M2. He sort of mashes M2 and M5 together in the program. And there was something else I was going to add on that. Oh yeah, and so this makes the beginning of the program more complicated than it would appear. Where at the beginning of the program, what you've got on the screen right now, at line 23, jump decker K, is something that's not reflected in algorithm M. He has to sort of complicate the beginning of the code to say, do some setup, and then jump to the end, where I'll actually do the test that appeared in M2 in algorithm M. So do some setup, jump to the end of the loop, do a test that will bring us back to the beginning of the loop, and then we can pick up.
Okay. I guess Arthur has a pretty good grasp on what this program is doing and how it's actually, the instructions are related to each other. Michael, Miguel, do you feel like you have a good grasp on this as well? Or should we just sort of discuss how it's actually supposed to work?
I don't know if I have a good grasp, but I have a quick question about the is stuff. So what it's doing there is saying that J is going to, whenever we call J within the code, it's actually always referring to the register 0.
Yes.
Right? Makes
Yes,
sense.
it's just a naming.
Yeah, exactly. So,
yeah.
And KK, what is the remark of A times K?
Anyone want to explain that? He's talking about line 11 on the share screen.
I'll explain in a minute, I'm just writing.
Okay. Yeah, so that is, it's essentially K is an index, right? So 1, 2, 3, 4, whatever, but we have to deal with octabytes.
Mm.
So the values are being stored in an array of octabytes. And so that's why the 8 times K, and he's given it a different name because it's no longer strictly K. So he's just called it KK. That's my understanding.
So in the sense that increasing by 1K actually means by 8, multiplied by...
because to get to the actual address of the next value, you have to add 8 bytes.
Yeah, if you want to jump 3 times, the same thing with the tetras before, right? You want to jump 3 places, is 3 times 8, okay?
For a tetra, it would be 4.
Yeah, no, that's what I meant, like, from the jump stuff that we discussed before. So if K is 3, is 3 times 8, basically, and that's the gotcha.
Yeah, that's so we have the base address, And then we have an index, which is k, but the actual address needs to be multiplied by 8. Yeah, so that's the 8k. Anything else before we step through?
So that the necessity for this KK variable is something that I brought up 2 or 3 weeks ago, saying I'm used to addressing modes on things like x86 and PowerPC and so on, where we could just say I'm loading from x0 plus 8 times k. And in MMIX, I still don't really understand why Knuth separates that into 2 different instructions. There's the one that loads the sort of effective address. Like I can do x0 plus 8k and put that into a register in one instruction using the add 8 instruction. And then I can load from the combination of that register and one-time sum at any register using LDO. But if I want to do those 2 instructions like together in a single instruction, I can't. And it actually ends up being more efficient, even though it's incredibly confusing, but it's actually more efficient to just keep k multiplied by 8 the whole time. And when we want to add 1 to it, we'll add 8 to it. When we want to subtract 1 from it, we'll subtract 8 from it. And we'll just do that. And when we need to copy its value into j, we're going to divide it by 8, because j is stored in increments of 1. And I feel like we have to do all of this because we don't have that sort of LD add instruction that would allow us to do the multiplication in the same instruction as the load.
Okay, so, all right, so I'm going to step through the program. Now, he does point out that the code as it's written in the text is for a subroutine. And subroutines don't run by themselves. They need another program where there's code to call the subroutine. And so I found this code. There's a whole collection of all of these programs that are in Fascicle 1 and the MMIX supplement. They are available online and they're open source and free, so it's no problem using them. But this particular program is sorting values. So I just took it as is. I didn't really modify it to just do the maximum. So what I'm going to show you will look a little more complicated than it needs to be, because it's sorting a bunch of numbers. And in this case, I'll have 10 numbers. And it sorts this array by finding the maximum successively, and then you end up with this sorted array. But in order to run it, I did need like a main. So first, let me show you the main. This is the main. And if you remember, in MMIX assembly, this symbol or this label is required, the main. And that's where the program starts. So when it starts up, it gets 2 registers that are filled in. $0 is filled in with the argument count, and $1 is filled in with the address of the first argument string. And so when we do that, you'll see that this will have an argument count of 1 because I'm passing it a file that has those 10 numbers in them, and then it will run through the maximum. So it will run through the program and call maximum. So hopefully my file is fine, and let me run this. Why does it say 0? Oh, maybe I don't. Let me see if. Oh, okay. In this case, I actually didn't need the command line because this program expects to read from standard in. So what I did was I created a file that it'll use as standard in because there's no way to actually pass, um, sort of like byte standard in to this visual debugger. If I had a command line, then I could do that. So yeah, so argc, which is over here, this $0 is 0 because there's no actual command line, but it will still read from standard in. Okay, so we are at the beginning of the program, and now let's see what happens. So the first instruction is this address that we're filling in this register. So T is the temporary register. Typically, the temporary register is going to be 255, but let's just confirm that. Yeah, so over here you can see it's 255. So this is a convenient global, the first global register, and it's really convenient to it because it's always there and pretty convenient to use as a temporary register, temporary store. Okay, so we have this. What is it doing here? If anyone wants to explain, if they've already understood this stuff, please feel free to, start.
Let me check my understanding here. Okay. If I understand correctly, this code that you've got on the screen right now is setup code. This is not the actual algorithm yet, but you've written a little driver program here to read some input from standard input and store it into an array. And then you're going to actually call this subroutine. I feel like if I were doing this for like pedagogical reasons, I would have just set up the array, just hard code it, store some octabytes into some area of memory and then just go rather than doing all this file reading stuff. Because we have not, even in the ones I missed, we didn't cover get a and trap and so on, right?
Yeah, it's coming up right away. That's actually the second program. So it's pretty straightforward once you know it, but you're right. Like this is reading ahead a little bit. So if you haven't actually read this piece, then all you need to know is that there's this function fread, and it allows you to read from standard in this case, which you can set a file to be used as standard in for the visual debugger. But the main point for fread is that it's going to read bytes from a source file or some sort of input, and then it's going to fill some buffer, some region of memory with those bytes. How does it know what buffer to fill, and how does it know how many bytes to read? The way it knows is you give it an address, which is this get a. At that address, it expects 2 octabytes. The first octabyte is the address of the buffer it's supposed to fill. The second octabyte is the number of bytes it's supposed to read. So you prepare those 2 parameters, you make this standard trap call to fread, and after the trap, that buffer will be filled with that many bytes. Let me show you where the parameters are. So this now also refers to what he calls, what does he call these? Local symbols, I think. I don't remember the terminology. The numbered F, B, and H, and yeah, something like local symbols or local labels or something like that. But the idea behind these local symbols or labels, if you notice, like if you go back up here and you look at, this instruction is labeled maximum. This instruction is labeled loop, change M, decrement K or decrease K. And the idea here behind these names is that they are significant names. They are, important names, and they need to stick out, and they need to be understood in sort of at a global scope in some sense, right? We need to know that this is the maximum subroutine. Knowing that there's a loop that starts there may be important for the algorithm. Knowing the fact that we are changing the maximum at some point, that could be important to know. So he's actually used names for those. But then he says, many a time, you don't actually need to come up with a name, but you still need a label because you need to somehow reference that address in some other instruction. So how can you come up with some temporary names? This is his mechanism for temporary names. Not only are these, they're temporary in the sense that I shouldn't even call them temporary. I think the right word is really local. They're not temporary. I mean, they're going to be there, but their interpretation depends on how you use them. So the first thing to understand about these local symbols is that the only name or local name that you can use as the actual name is the one with the suffix h. So that's the actual identifier. It has to end in h, and then there's a number before it. This number is a relative number, and it gets a little complicated, but you'll see how it works. So it can be any number, but its use and its utility comes from the whole system. So this thing is labeled 9H. So this means that this is like the local symbol 9 that is defined here. This is the address. When we say 9, this is what we mean. 9 here. H stands for here. H-E-R-E. Okay, so when we use the local symbol 9, we can reference it from somewhere before or somewhere later. If we reference it from before, we have to say 9F for 9 forward. And if we reference it from somewhere below, then we have to say 9B for 9 backward. And the 9 refers to the closest 9 that is located forward or backward. Okay, over here, it's not a problem because there's only one 9, right? So there's no ambiguity, there's no, conflicting 9 that exists. So we don't have an issue in terms of that interpretation, but this is something to keep in mind when you read the programs. So 9, when we say 9F here on line 50, we're referring to some 9 symbol in a forward direction, meaning higher addresses or lower, in the program, that is labeled 9H, and it's the first one. It's the closest one to line 50 over here. That's the 9 we're referring to. There could be other 9s even further down, but this is the one that will be used. Is that pretty clear? But again, these are like a lot of these practical things that make a lot more sense when you start working with it. And in the beginning, it does feel a little complex. But anyway, if we go to 9H, right, I explained that Fread expects 2 parameters, 2 octabytes. So if you look at that 9H it's not really an instruction. This is one of those assembly language directives. It's placing an octabyte at a certain location, which is after the program. So you'll see the octa directive. Now, each one of these octa or wide or byte directives, they can actually take any number of arguments. And that's how many of those type of values will be placed in memory. So you can see a comma here, right? That comma is separating 2 octabytes. So if we look at the first one, it says x0 plus 1 shift. So yeah, this is again, there's no parentheses here, but it's really this thing, which is 1 shifted 3 to the left and then added to x0. So what is 1 shifted 3 to the left? It's multiplication by 2 to the 3, which is multiplication by 8, which gives you 8. And then we add that to big X0. So what is big X0? Big X0 is this thing. And big X0 is going to be whatever at was at that point. Okay, so what is at line 5? At is whatever the current address is. And if you look at this very first directive, that's the location directive. It essentially sets the address. And from that point on, everything is happening from that address onward. So the data segment is a very special address. It's the part of memory that programs are allowed to write to. And it is 0x2 and then all zeros. So that line 3 is establishing the current address to be the data segment address. So when big X0 over here on line 5 is told that it's going to be at, that means at, which was the data segment address, becomes the value of X0. So that's what X0 is. In this case, it's not a register name, it's just an address value. So back down here, when you say this, that means the buffer is that X0. It's actually X0 plus 8. It's like the next octabyte after X0. And then this one, this is N shifted 3. And if you look at N back up here, that was 10. And so we're saying we want to read 10 octabytes. Each octabyte is 8 bytes, and that's why you have the N shifted 3 over here. So that's the fread. That will set up the input. It will fill the buffer, and then there's some extra stuff over here that I'm going to skip over. And at some point, this is going to happen, which is the actual call to the function. So this is the push jump instruction. And this is, pretty much the standard way of calling a function, but there are other ways of going to another function that are discussed in detail in the section on subroutines, but this is the typical way. And this is again something that we're just going to take at face value right here. But when you call a function, typically you want to pass some parameters, some values for parameters that the function expects. And then the second thing that you will typically need is to somehow get the return values from the function. So over here, when you say push J1, maximum. This means save some local registers. So push some registers onto what's called the register stack because I don't want them to be overwritten when we enter the function, and then call the function. How does the function get the parameter values? It is based on this number here. So since this number is 1, what it means is that the number after 1, which is 2, that becomes the first register 0, or that becomes register 0 for the subroutine. So if this code puts a value in register 2, the subroutine code gets that value in register 0. So that's the setup. And yeah, I know that this is a lot to take in, but that's the way subroutines will work. So let's do that. Let's step through this, and after the read, I should be able to see my data segment here. And if you look at the data segment, you'll see these values that are random numbers between 0 and 9, I think. Is it between 0 and 9? Yeah, I think they're supposed to be between 0 and 9. So I just created some random input, and so the first value that you see is 7. Then there's a 1, there's a 6, 5, 4, 2. Oh no, it's between 1 and 10. It's between 1 and 10. So that's an A, hex A, which is 10. And then there's an 8, there's a 3, there's a 9. So that's what the fread did. It filled that memory with these values. Okay, so now we will jump into, okay, I want you to keep an eye on this area here where it shows the registers. Let me expand this a little bit. There. Okay, so when we do the PUSHJ, what will happen is that the current registers 0 and 1 will be saved, and you'll see that represented in that top right panel with duplicate zeros and ones. So you'll see kind of like a stack in there. So let me step here. Okay. Now we are at maximum. We're at the subroutine maximum, the beginning of that. It's a little more complicated than I explained. So $1, which was the old register 1, is saved as this 1 here. So what you will see is the old register 0 at the top. Then you'll see a dash, which separates the two register sets. And then you'll see the bottom portion is the set of registers that are local to maximum. And as we change and we work inside maximum, you'll see that bottom set expand and change. But the top set is not going to change because those have been saved. Okay, so the first thing is that KK index is being set. It's taking the so what is in $0? So this is the parameter that's being passed to maximum. So this parameter is 10 because that's the number of numbers or number of integers that we want to process, the size of the array, and also this was the value that was set in the main function before we call the subroutine. So now we're seeing this 10 here in $0. So the way the algorithm and the program work is that it works backwards. It's starting at the last index, and then it's going to find the maximum going backward from 10 to 9 to 8. The other interesting thing is that if you're coming from a C, C++, pretty much most modern programming languages, arrays indexing begins at 0. So when you pass in the size of an array, typically you expect the last index to be size -1. But here in Knuth, I've noticed that a lot of his algorithms, and definitely all those programs, they're using array index based on 1. So the last index is going to be the size of the array. Okay, so we step over this one, and now KK, you can see, so KK is $2, and you can see $2 becomes 80, which is the offset in bytes that you would need to get that last entry, right? Because the address has to be in bytes. So $2 is 80, and then we are going to take the actual integer at that location in memory, and we're going to load it into the register that we're calling M for maximum, which is register 1. So step into this, and you can see that $1, the current maximum is 9. So does this agree with what we see in memory? Yeah, because down here, 9 is indeed that last entry in the array. So now we've got 9, which is the current maximum, which is the last index, right? So this is sort of initializing the maximum. And then we are going to start working backward into the array. And for that to happen, we go to this instruction where we're going to start decrementing the index and then run through the loop. So the next instruction is this decker K, and you can see that this is that the different ways that you can sort of use the target address with jump instructions or branch instructions. So if you have a name, you can just give that name, and step over this, and we're at decker K, and this is a subtraction. So we will subtract 1 from our current offset, and you can see that $2 became 72, and then we're going to do this branch. Anyone remember what the PBP is?
Probabilistic something?
I'm sorry?
Probable branch if
Probable branching.
positive.
Yes, exactly.
That was very confusing to me when I read it, by the way.
Yeah, it is.
I know that it happens in modern CPUs, and I understand the idea of why would you want to do that, but not the why it works or how it works.
Anyone want to briefly explain
Sure.
what's the benefit of probable branch as opposed to just a branch?
Wait. I understand the benefits of probable branch. I
okay.
don't understand that, like what makes it okay. When you say probably jumped here, and then so it means this is what I mean. This is what I understand. What I understand. It means jump here, and you might want to stay there, most likely, but you might want to jump from there because that wasn't what we wanted really, right? But there is most likely we want to jump there, so jump already. But I don't understand how it actually works.
So basically, the probable branch instructions are not necessary to the operation of the computer. We could just say B instead of PB, and it would work fine. What probable branch lets the computer do is it tells it, even before it's gotten to this instruction. Remember, this is a conditional branch, right? Like sometimes it's going to be taken and sometimes it won't, and the computer does not know until it reaches this line and executes it whether the branch is actually going to get taken or not. So if you have a complicated modern computer that wants to do things like speculative execution, if it wants to be reading ahead, going ahead of where the execution really is, and saying, I'm going to start preloading these instructions and maybe start decoding them so I can get a jump start on actually executing this bit of code. It needs to know whenever it sees a conditional branch, well, now I've got a fork in the path. Should I continue speculatively preloading stuff over here, or should I be preloading stuff from this path? I don't know which it is. And so if you have a computer that is modern enough to do speculative execution and prefetching and preloading, and yet at the same time not modern enough to just have a branch predictor, if you're in that weird sour spot between those two things that were invented at the same time, yeah, I don't know why Knut thinks this is interesting. What you can do is have the programmer tell the branch predictor what to do. So here the programmer is saying, hey, computer, when you get to this point, you're going to get here twice, right? You're going to get here once when you're skimming ahead real quick, trying to do speculative execution, trying to do prefetch. You're not going to know whether the branch is taken or not, but I'm just going to tell you probably usually it's taken. So just go ahead and act as if it's taken as far as prefetch is concerned.
Okay, so what you're saying is that
we're going to execute it and find out which way it goes.
So what you're saying is that the computer, I don't know how to call it, the whatever it is going to run this while we will load the code into the runtime or the programming or the computer, the CPU, it will in fact start fetching and branching before you even get there.
Right.
And when you get
branching,
in the same way that in this, the thing we're doing in this meetup, right? Zartaj tells us, go ahead and read this part of the book. But you can, if you want, be going ahead and reading ahead. But you don't know until he tells you. You don't actually know what part of the book to read next, right? And so normally it's pretty obvious. We just execute it in sequence. But when we get to an obvious branch point, well, now I'm not sure which part to read next.
No, that makes sense. The part, I mean, at this point, it's just curiosity. I don't think it's going to add much, but what I try to understand is that operationally, what you're saying is that the artifact itself will look at the code and start branching. There is some secret logic that is going to do this potential branching.
Yeah.
You are only signaling in this case. You are signaling that it should try to do that, but you really you have no control over other than just signaling it.
Let me ask you this, Miguel. As far as your understanding goes, when we're at this point at line 44, what are the two possible next instructions that could occur?
Okay, so what I see is either K was.
You can just give the line number. You can give the line number.
Yeah, it's 44. Yeah. So at that point, what I see is K was decreased. Therefore, it could be it was 0 before, or is negative now. So if it's positive, it still hasn't reached 0 in the previous decrease. Just keep looping. So in that case, we'll go back to 26.
Okay.
Otherwise, keep going.
Which would be line 47.
47, indeed.
So think of a computer at this point, at line 44. It's running the instructions. It's at line 44. What we know is that the next line to run can be either 26 or 47. Now, if we were just like a very simple-minded computer, that's fine, right? At this point, we're going to see what the net result of 44 is, and then we'll say, hey, line 47, you're up. Or we'll say, hey, line 26, you're up. Think of each line sort of waiting to be called, right? But if you're a little clever, or if there's some overhead involved in this sort of like, hey, who's the next line, right? So you could have the guy who's going to be next already standing next to you. So they don't have to come to you and say, okay, I'm ready to run. You know, I'm line 47. It's my turn. So I'm going to walk over to you and I'm going to do what I need to do. So a lot of the modern computer pipelines work that way. There's some overhead involved in determining which instruction is going to be run next, and then actually running it. And so if you have some way to predict what that next instruction is going to be, that's pretty reliable, or at least probabilistically more likely, then you have the chance of reducing that overhead, which is what Arthur was calling prefetching. So that's sort of the idea. But it is a very deep topic. I will also point out that the instruction is really useful because a lot of times these things are being generated, or not a lot of times, but pretty much always, this is being generated by a compiler. So a compiler, can generate, or it can be given certain options where somehow the programmer, or through some testing framework or profiling framework, is able to generate these instructions that are now probabilistically, more likely to run faster. That's the idea. And here, why would we want to do this? Because most likely we have a whole bunch of numbers, and most likely because it's a sequential algorithm that's going to run through the entire array. So 9 out of 10, if I have 10 values, 9 out of 10 times I will be taking that branch back to the loop, and 1 out of 10 times I'm going to fall through to the next one. So it is beneficial in a lot of situations. So that would be how I would explain it.
Cool.
Okay, so in this case we know that it's going to go back up, and we'll just follow that. What happens here? We are now in a position to actually compare the next value with our current maximum. So we load the value itself, which we can see from the memory view down below that it's going to be 3. So we should expect to see a 3 in the XK register, which is $3. So that's where it shows up. We've got a 3 there, and we do a comparison of the 3 and the current max, which is 9, and we end up with a negative value. And what this is saying is this is another probable branch. Probable branch, we can just ignore the P for now, right? So it's like branch non-positive. So non-positive means it is negative or 0. So if it's negative or 0, we want to take the branch, and that's because in that case the new value is still less than or equal to the maximum, so we don't need to change the maximum. So let's just keep on doing that, and we'll see when the maximum actually changes. So it'll be the next one after 8. So 8 is not going to change the maximum, but at this point we should change the maximum, because now we've got 10 loaded in register 3. We do the comparison, and $255 is now 1, which is positive, so that should change the maximum. So that's what's going to happen here. Here you see the set instruction, right? So this is now basically setting a register to the new maximum, and we should see a 10 there in $1, which we do. And then we just keep on going. So, right, we just keep on going, and at some point we are going to reach the last or the first index, which has a 7 in it. So this should be the last iteration. Okay, so now we're done with the maximum finding loop. We have our maximum in $1, right? That was the register that we're calling M, right? So over here, this is $1. So when we say pop 2, 0, this is the return. This is the equivalent of a return statement in a higher level programming language. It has 2 parameters. The first parameter, which is the number 2 in this case, says how many registers, how many registers will contain values to be returned. So when you say 2, I believe it means that 2 registers, which is register 0 and register 1, will have the return values. I think that's right. But again, these are things that I just read in the last few days. So some of them, I'm a little fuzzy on the details. But
can I ask you a question about
yeah,
that?
Yeah.
So reading about pop, it says, so what I understand here is when you do pop, will go, actually the X, I don't know where it goes, but then the next add will become whatever was in the register RJ plus, so basically the next, RJ plus some jump. So it's like, it's jumping.
I'm glad you brought that up because I totally forgot about that back here. Well, it wasn't really relevant till now, but yeah, when we did the PUSHJ 1 maximum, I told you that the 1 tells MMIX something about which registers should be saved and not allowed to be written over by the subroutine. The maximum obviously is where we want to go, but then what tells it where to return? How does it know where to come back to? That's this register J over here. So when I did the push J1 maximum, this thing, RJ, got set to this value, 140. And 140 is the address of the instruction after push J. So if we looked at the address of this guy, that would be hex 140. So RJ now retains the return address, the return location. When we're in the subroutine and we want to return, the second operand tells you the offset of the default return address, hex 140. So if you just say a 0, that means hex 140 plus 0. So yeah, whatever that default return location was, just go back there. But you could have other offsets here. So you could say 4 or whatever, if I believe, I'm not sure how exactly he uses this because I haven't read that far ahead, but I believe he uses this for multiple return locations. So a subroutine doesn't have to return to one fixed location. It can actually return to different places back in the calling program. But typically for straightforward programming, I think you would always just see a 0 there.
Makes sense. And just one last question about these registers becoming marginal, which I didn't understand when I read it, but I think now I got it. But I want to make sure.
Okay, that's more than I can say, but yeah, go ahead.
I mean, I got the point, not necessarily the mechanism. So what I understand now is that, let me see if that's true. When you go into, when you do the jump into the maximum, everything that was there becomes marginal, means that now the zero register is actually not the originally zero register. It's just like some whatever number, but from your subroutine perspective, it is in fact the zero register. And when you return it, so the marginal registers, I understood that's what I meant. Like there is some number from which below that number the registers are not, they don't exist basically. They begin in zero for the current executing code, which could be a subroutine. And when in this case when it returns, now all the previously marginal registers or whatever, they become visible again. So whatever was, so now the zero is going to back to zero. If that makes sense. Is that what? Does that make sense? So I don't understand what the 2 is in this case though.
Anyone
But
jump in, clarify your own understanding? Agree with Miguel, disagree with Miguel?
Personally, I'm just waiting for us to get to the part of the book that talks about the push and pop, because I don't really get it yet either.
Okay.
I don't
Okay,
think it says.
so maybe it's worth spending more time on the details behind push and pop.
I don't think it says anywhere what happens. It could be that other registers, that when you push 2 registers like that, that what used to be $2 is reassigned to $0, and that would kind of indicate that when you're in a subroutine, you don't really have 255 registers anymore.
Yep.
Or it could be that they're just saved off somewhere into some sort of internal stack that you can't access until you get out of the subroutine. I suppose that's possible too.
Yeah, that's my understanding. My vague, I don't understand the detail of it, but essentially it's a register stack. And I believe that
stacks aren't infinite. You can write a recursive program, so there must be a limit. I mean, well, this is theoretical. So
a stack is by definition infinite, and if you run into a hardware limitation, that's your hardware, right? It's the same on Intel, right? Intel has push and pop.
wait, we haven't read about the marginal registers. I remember reading about it. I just don't find it.
It was very early on. It was like,
It was very early on. Okay.
yeah, one of the very first sections where he describes the total number of registers, and he says that there are 3 kinds of registers. There's local registers that are actually being used in code, and then there are the global registers that kind of live beyond, a single context, and then there's the registers in between. These are marginal registers, and they get turned into local registers if you use any one of them. In fact, any register below a certain number, if you've written to it, becomes a local register. Or from the other end, from the global register end, you can start using them as well. So think of the lowest numbered registers as your local registers, the highest numbered registers as your global registers, and everything in between that's being squeezed as you start to use more global registers or more local registers. And pop is sort of releasing those things. It's releasing some of your local registers and allowing them to become marginal again. But it will depend on like where the subroutine was called from and how many registers were saved. So that's where it gets really complicated. So yeah, again, this is like, it does bother you a little bit, because it's when you read this stuff, you'd like to understand exactly what's going on, but we do have to take certain things on faith if we're going to deal with the fact that some of the code will be subroutines, and to really work with it, you need some kind of setup or driver program. So some of these things just work. I did want to actually show you how specifically a specific example of the register renaming, etc., outside of the context of an algorithm. I mean, if you want, I can do it right now. I didn't plan to do it right now, but I do have that code loaded. Do you want to do that, or is it already a lot for today?
So no. So I just to verify something. Do you have $2 zeros there?
We have $2 zeros, exactly, because we're inside one subroutine. And so now we have saved the location or the context where we called the subroutine, which was the main program. It had its own $0. When I
Yeah.
did
So
the
that's what
PUSHJ, I told it to save a certain number of those registers on the register stack. So what you see up here, this is mains $0. This is not going to change until I go back. There's no way a piece of code can affect those registers anymore.
Nice. No, that was my intuition. I just wanted to
Yep.
verify that was exactly what was happening.
Yeah.
Exactly. Nice.
Yeah. So that's about it. Like when you do the pop, we will return back to line 64 here, and you will see that stack go away. All of these 4 registers will disappear because subroutine maximum will no longer exist, and you'll see the values there. So step, and that's what happened, right? So $1, remember, is because I did the pop2, it actually allowed me to return 2 values. The first value, which was the index or the offset into the array, where the sorry. The first one is the maximum value, which is 10. The second value, the second return value, is the index of the maximum value. So that's here, 7. And $0 is that original $0 that was saved. So that has not changed while we were in the subroutine. So now it's back. The way the return values work is that whatever registers were saved, then the registers after that, we just saved 0, and after that get filled in with these values, so 10 and 7. So there's still some stuff that I'm trying to work out, and that's why I wrote up this sort of sample code for me to understand like how this thing is actually working. There's a hole. So Knuth literally calls this a hole in the register stack. You saw that there's a dash there. I think that's what he's referring to, a hole when you do make a subroutine call. And I'm a little fuzzy on what that hole or why that hole is there and what its purpose is, but I'll probably figure that out over the next week or so. Yeah, so that's about it. You know, I think the main things that are kind of interesting and new in this stuff is the local symbol thing and how do you use that and what it means, and then the register renaming, the register stack, you know, how you set up parameters to be passed to a function, how you can get back return values, and then obviously the algorithm itself in terms of branching and looping, how that works out. So if you care, I can quickly show you the program that I uploaded to that I wrote in C. That's the equivalent of this, and you'll be able to get a sense of how this thing would map to a high-level language. Okay, so here, um, is everyone somewhat familiar with C and pointers and addresses? If you're not, let me know and I can explain. But the star here is for dereferencing. So whenever you see a star, that means that there's some address involved, and we're actually going to refer to the location of that address. And then if you want to actually work with the values, you would use the star on that. But anyway, I think what I found interesting when I was writing the C program is trying to figure out, while staying faithful to the algorithm and to some degree the program, the MMIX program, is, how do I use like higher level constructs like for loops and other stuff. C doesn't have a lot of really high level constructs, so it's not a big problem, but I wanted to avoid labels or go to, and I didn't want to do like a literal translation. Uh, so sometimes it gets a little tricky, like in terms of um, where is the initialization going to happen, and how do I actually map a particular instruction that he's jumping to from different parts of the program or the algorithm. How do I represent that in a more structured way? Um, but I did find this really interesting, and that's why I was mentioning that this is another interesting project that I've been now thinking about, is just writing C programs for all of the algorithms and programs, and certainly all the MMIX programs that we'll see over time. I think that could be, just for myself, it's good practice, but I also think a lot of people who have this criticism of Knut that, you can't understand the assembly language easily, and, why didn't you use a high level language? Having that resource, I think, could be helpful.
One thing that I would do if you're going to do this for general consumption is, I think having M and J be pointers here is, as you say, there's a spectrum of how much do I alter this to conform to C idioms as opposed to, but the way I would think of it is that M and J here should really be global variables, right? Because they're registers in the original, right? So things that are registers in MMIX.
Yeah, but they're local. They're local registers.
Should become variables in C.
But they're local registers.
They go away when you leave the
So
subroutine.
yeah, so to me that justified making them. In general, I just wanted to make, I didn't want to use globals like just generally out of my own preferences. I wanted to avoid that. So that's the balance that I was sort of referring to. Like initially, I did start out using, for example, the array. I made that global, but then I decided that I don't really want to do that. I would rather pass. So there is some things that I'm introducing in this C version that don't naturally map onto the MMIX or the actual. I mean, in the algorithm, there's no global or local or anything like that. So it's all about then comparing it to the MMIX program. But even there, you have a point. Like, I don't want to be too far off, because I want people to look at this as an aid to understand the MMIX program. But regarding the pointers versus variables, that's again a fair point. I was, kind of undecided where I should make something just a value and use that. But when I looked at the algorithm, when I looked at the MMIX program, I felt in this case it made more sense to have it as a pointer, because the otherwise I would have to do some kind of copy of something. But yeah, I mean, these are things that you can decide one way or another. I did want to stick to both, primarily the algorithm, but secondarily the MMIX program as well. But those are the things I found interesting. Like how do I do that? If I were just writing this program from scratch, I wouldn't necessarily write it this way. But trying to maintain that one-to-one correspondence, and this is a very simple and short program. Now, how is it going to be when we deal with more complex algorithms? That's going to be pretty interesting. But yeah. So I think that's quite a lot for today, but we will. I did want to. I mean, we're kind of near the end of the MMIX portion, and we've covered all the basics essentially by now. And so the next meetup, or maybe the meetup after that, we're going to start with the main content in Volume 1, Chapter 2. And, if you guys want to think about, like, if there's something about MMIX that you would like me to cover earlier than later, like I'm now thinking that maybe subroutines are things that maybe we should cover a little more relatively early on, at least get it out of the way. But if there's some other stuff, or there's other topics or sections, maybe further down that would determine the direction that we take earlier on, do let me know. I think early on there's not a lot of leeway because there's some basic stuff that we have to go through. But probably after 4, 5, or 6 sections of the initial stuff, there's a lot of choices there. So you can say, okay, I would like to do this a little earlier or do that. So yeah, you can look at the meetup schedule, the tentative schedule that I have up on the GitHub repo. But yeah, essentially we'll be going over arrays and lists, singly linked lists, doubly linked lists, circular lists. Then we will probably come back to MMIX and subroutines and coroutines. And then we'll go back to trees. So then there's like 3 or 4 or 5 sections on trees and algorithms on trees. And I think after, I believe it's like 10 or 12 of those sections, we may be able to tackle some advanced sections, possibly from volume, most likely from Volume 3, which will be like sorting and searching, and then there's a lot of stuff there, some basic sorting algorithms, some basic searching techniques, which could be another like 6 to 10 sessions, and after that we could be tackling sections from Volume 4 or the individual fascicles that he's released. So that's pretty interesting. But yeah, any thoughts, comments? Regarding
I would like to go on to the algorithms and skip the optional stuff in MMIX. MMIX to me is kind of like, it's not real, and it doesn't really correspond to today's microprocessors. We don't need to know it in detail to get through the book.
Okay.
We can always come back to it.
Okay, yeah, that sounds good. So we can defer some of the more optional stuff till even later.
It's just my vote.
No, yeah, absolutely.
I agree with that.
Every vote counts. Yeah.
we should only really come back to other MX stuff if an algorithm requires it. You know, if an algorithm uses some weirdness, as I'm sure that they will, because he loves it.
Yeah.
Yeah, they might have to revisit.
Yeah, that's why I was even bringing it up, because if I felt like we could get away with not reading some of the finer points, then so I'm trying to defer it as much as possible. But there are some algorithms that do require some of the other stuff. But yeah, even then, again, if you're willing to take some things on faith, and when you're reading some code and you say, I'm not too concerned about this little piece, then that may be good enough. So regarding the project, so I was actually thinking that at some point I may start on one of these like side projects, like just writing the C programs, or maybe developing a browser-based debugger or MX simulator. Um, um, and so I thought that I would have like extra meetings for that. So these would probably be weekday nights. They would be completely optional. So this would be stuff that, again, if you completely skipped it, it wouldn't affect our Saturday meeting. But if you were interested, then this would be, just some other thing that I'm doing. So these would probably be weekday nights, probably 8 or 9 p.m. New York time, um, and I just wanted to have some time where I could just work on this stuff, and probably will be live stream. So I will probably just announce it on YouTube or something, and then work through these things. So I will post those probably on Meetup as well. I'm not totally sure about that right now. I may just try something, see how it goes, um, and again, just stuff that people may find useful if they're interested in some of these other details. So
I think there's already an open source program out there that runs all kinds of languages in your browser for it's for learning all kinds of higher level languages, and they have modules that people develop and put up for new languages all the time. They've got, it seems to me that it has Python. It was originally running Python, but I heard about it running Java and the Java languages.
I'm not aware of anything open source that there's a lot of coding platforms
Yeah,
that let you do that.
I listened to a podcast on this, and they went into quite a few details about what parser they chose and how it works. But for the life of me, I don't remember the name of it.
Okay. Yeah, if you remember, or just whatever next time. Um, so Arthur is saying REPL it or Godbolt. Uh, so Godbolt, as far as I know, doesn't actually run programs, does it?
It does as of about a year ago.
Oh, really?
Yeah.
Okay. So and
Neither of
REPL
those are it. So there's another one out there.
it, is that open source?
I have no idea. It doesn't really look like it from their website.
Yeah, I
Another one that's
remember looking at it, but again,
okay.
I didn't recall anything open source that worked like the way the coding platforms do. So many coding platforms, HackerRank, and they let you do this stuff.
I'm sure the podcast that I heard this on was one called Talk Python to Me.
Okay.
There's also
So
CIA
if you look back in there, you may find it.
Okay. Yeah. So
That's
maybe
all I remember about it, though. Huh?
yeah, maybe that's one possibility, that you somehow extend this open source thing. But I don't know where this open source thing would be hosted and how you would. What I was thinking was that you could have something local. So you
Yeah,
could
yeah.
essentially this debugger that I'm showing you, which is a desktop application, but you'd have a browser-based version.
Yeah, this open source project is written in TypeScript. It runs on your locally on your browser.
Which one?
What I was talking about,
what you were
I
talking about.
remember,
Okay.
it runs in TypeScript. It doesn't need a host. I mean, GitHub to host the source code, I suppose. But you download it and you install the modules that you want to work with. If it's not,
Okay.
I think it was natively Python, but
Okay.
I maybe even be wrong about that.
Okay. Yeah, that definitely sounds interesting. So, but the key thing here is that whatever it is, it will need to support this WebAssembly build of the simulator and the assembler, because that's basically what we'll
Oh
have to run.
yeah, oh yeah. So WebAssembly as in .NET.
No, WebAssembly is a JavaScript way
Okay.
of running C++ code, essentially. So since the simulator and the assembler are available in C, so it works as C++
Oh, I
as
see.
well. You just use that, but then you create a wrapper around these
This may
tools.
be a derivative off of that. What
Yeah.
I'm talking about. Yeah, maybe a derivative off of that somebody took
Oh,
and
no,
ran.
no. I mean, I meant that for MMIX specifically, if we wanted to use MMIX in the browser, we would need to do that. Somebody would need to do that.
Yep. Gotcha.
So if that can be plugged into a more a sort of a bigger framework that lets you work with different languages, then that could be interesting too. But yeah, my own feeling is that generally these things, if you try to plug something into a another general framework, it can be a lot of work just trying to make yourself fit into their holes. But yeah, I mean, again,
On
it's just
the other hand, I don't think anybody's going to be want to download a web to do MMIX. They may be working with Python and learning Python and Scala and whatever, and they say, MMIX.
yeah, no, you're right. It would be very limited interest, but what was bothering me was that I thought that this visual debugger was available on all platforms, but it's not. It's Windows specific.
Oh
So
wow.
it would really just be an equivalent to this if it ever came about. So whoever would be interested in this, the visual debugger is sort of the audience that would be interested in something that's based in the browser. So very, very limited. Yeah, certainly. And those other languages, yeah, those have like more general purpose usage, and yeah, audience would be completely different. Yeah.
Yeah, but it would also be the audience would be students. I don't think anybody's going to use MMIX to develop anything seriously useful other than learning about microprocessing or
Well, in the context of TAOCP, right? So in the context of
probably only in the context of
yeah,
TAOCP, right?
right.
Is it used anywhere else?
It's not manufactured, but I don't
No,
really
no, no.
see.
I mean, is there another textbook or another course out there that's
Oh
not
no,
TAOCP
no.
that says?
I
I don't think
really
so.
no
I mean,
no.
when I studied for my master's degree, when I studied computer architecture, it was VAX that we used, and I was thinking at the time, I'm never going to use a VAX. And that's a lot closer to what I may actually use than this is.
Yeah, yeah, yeah. All right, guys. Thanks for attending. See you next week.